in number 87, we've got the beginning of it is conceptual. All right? We know that the kinetic energy of each block at the bottom is the same because the blocks are identical. That means they have the same mass. They have the same initial velocity. Okay? So they have the same kinetic energy. They have the same potential energy because they both start at what we'll call block 8 or height h equals 0. Technically, we should make that h0 go through the center of mass of the block, and then we measure between centers of mass. But we'll just measure to the bottom, assuming that those would be exactly the same thing. Okay? So now the first question is, A, when the block on the longer track, reaches maximum height, is its final total mechanical energy all kinetic, all potential, or some of each? So this one goes up to here, and what does it do when it reaches its maximum height? It comes instantaneously to rest, right? So if it's instantaneously at rest, here V final is equal to 0. What is its energy? Kinetic energy is 0, right? So that means, kinetic energy is equal to 0, so mechanical energy is all potential energy, isn't it? Okay? So now over here, in this situation, that's part A. All right, when block on the shorter track reaches the top of its trajectory, after leaving the track, so it's like a ramp, right? Is its final total mechanical energy all kinetic energy, all potential, or some of each? Some of each. Why? Because what happens when it goes off the ramp? And wait, doesn't it reach 0 when it goes to the top? Only its y component. Good. All right, that means that it's got some velocity in this direction, doesn't it? Which is going to be the same as this y component, or I'm sorry, x direction. I said y. All right, which is going to be the same as that right there, right? Which is going to be v naught cosine theta. So that means that it's some kinetic energy. All right, so v final is not equal to 0. So it does have some kinetic energy, and it does have, certainly, some potential energy. So it's got a little bit of both, doesn't it? Okay? So that's the quick answer there. So which is the greater height above the ground? H, here, which is green, or this H1 plus H2. I don't know why they do that. That's where it leaves the track, I guess. But we could have just said H prime, right? That or this. So blue or green, which is going to be greater? Green. Green has to be greater, right? Because we have to save some. In other words, we got an energy budget that's at the bottom as kinetic energy. Okay? So if some of this over here is kinetic energy, that means its potential energy can't be as much as this, because over here in the green, it's all potential energy. Does that make sense? Yeah. All right, cool. All right, so now, if we give initial speed of each block 7 meters per second and a theta equal 50, the block on the shorter track leaves the track at a height 1.25 meters above the ground. Find the height h for the block on the longer track and the total height for the shorter track. All right? So what we're saying here is, the first one that we're asked to do, is what is the one for the longer track? All right, so this one's pretty easy, seems like to me, because if we start down here, kinetic energy is equal to 1/2 mv squared. Potential energy is equal to, and what is it at the beginning? 0, okay? So we should do that, mv naught. We'll do all those knots, okay? Because we're feeling naughty. All right, at the top, the potential energy is equal to, I already made that joke today, so now it's on here twice, mgh. All right, and the kinetic energy is equal to what? 0. Good. All right, so this is another situation. Usually we do it in reverse, where we slide it down and we get that the velocity is equal to square root of 2gh. Here we're going to get h in terms of v. So now we got mgh is equal to 1/2 mv naught squared. So now what we're looking for is this h. They gave it as capital H. I hope that doesn't confuse anybody. All right, the m's cancel out, and we get that h is equal to v naught squared over 2g. Does that ring any bells? Yeah. For what? Max height. Max height for projectiles. Good. Like we could just shoot it, and we've got that, and that should be, it would be v naught y, right? But in this case, Good to go. All right, so what do we have for our initial velocity? Wasn't it 7 meters per second? Yes? All right, 7 meters per second, and theta's 50 degrees. Wait, do we have to worry about theta?
No, it's the same.
All right. What about g? Wait, just kidding. All right, so 7 meters per second, and I know I messed up the precision there, over 2 times 9.8 meters per second squared. Dimensional analysis, meters squared per second squared, meters per second squared leaves meters. We're looking for a height, so we're good there. So 49 divided by 19.6, got to be about 2.5. What is it? All right, 2.5 meters. All right, so it goes 2.5 meters. So now we're saying that the one that flies off the ramp that has a height, what does it say? Leaves a height at 1.25 meters, leaves the ramp, okay? So that should be less or more, did we decide? It should be less because it retains some kinetic energy, okay? So let's go ahead and do our calculations. What is the height? All right, so in this circumstance, we have at the bottom, same thing as before, potential energy is equal to 0. Kinetic energy is equal to 1/2 mv0 squared. At the top of its trajectory, okay, because it's a trajectory now, it's not just coming to rest, we have potential energy is equal to mg, and I'm going to call this capital H, okay? They call it H1 plus H2. All right, we call it H prime. Let's just call it H prime, okay? And that's what we're solving for. It's the same as what they call H1 plus H2. And kinetic energy is equal to 1/2 mv squared, where v is the velocity at the top of its trajectory. And we'll figure that in a second, after we do our algebraic solution here, all right? So we know that 1/2 mv0 squared. Now, I just went through all these making one majorly important assumption, and what is the assumption? What are the forces that are acting on it? We've done all of this under the assumption that only conservative forces are acting, or doing work anyway. Only conservative forces are doing work on the object. So what forces are acting on the object as it's sliding up the ramp? Normal force and gravitational force. That's it. Because the force that accelerated it, set it off at V0, is already done. That's not part of the problem anymore. Okay? But what about the normal force as it slides up the ramp?
Perpendicular, so it doesn't do work.
Good. The force is perpendicular to the displacement, so it does 0 work. So only gravity's doing work, so everything is conserved. Shouldn't have made that assumption without really talking about it explicitly. All right, so here it goes flying up the ramp, and then it goes and it's over here. Okay, so it makes that noise too. So 1/2 mv0 squared is equal to 1/2 mv at the top squared plus mg h prime. And now again, we're solving for h prime, right? So h prime, yeah, let's do that. Thank you, Catherine. Let's throw our red pen around first. All right, m. All right, so we got h prime is equal to 1/2 v0 squared minus 1/2 v squared, all divided by g, right? G. All right, we'll simplify that in a second. So now let's clean that up a little bit. We've got v0 squared minus v squared over 2g. Everybody okay with that? What's that? That looks familiar too. It is a timeless equation, just kind of moved around, but this is d, right? Nice. Good, John. All right. So now, what is v at the top going to be, though? H is, right. All right. So the x component of our v0, right? Because it retains that the whole time. All right. So h prime is equal to v0 squared minus v0 cosine theta squared all over 2g. There's going to be some fun math going on in here. Can you see it? Can you feel it coming? We're going to get 1 minus cosine squared. Get out of here. All right. So let's simplify here. We got h prime is equal to v0. What do we got? v0 squared minus v0 squared cosine squared theta over 2g. And from there we get h prime is equal to v0 squared times 1 minus cosine squared theta over 2g. How's that for fun? H prime is equal to V naught squared sine squared theta over 2g. Now we could just plug all our stuff in. What was our V naught? 7, right? 7 meters per second squared times sine squared of 50 degrees. You guys are working on this as I'm writing it, right? All over 2 times 9.8 meters per second squared. Again, meters squared per second squared divided by meters per second squared. Dimensionally is going to be meters. All right. So what is H prime? What is it? 1.47. How come we didn't incorporate that 1.25? What is 1.47? Is that our total height?
No,
That's
don't
the
even
height of
add
the
it.
that's the height of the
No,
arc,
no,
and
no.
at 1.25
It is
height of
your
the
H
ramp.
prime.
Okay, hang on, Nick.
See, I thought about that as we were doing it. 'Cause
Yeah, I
feel
did
like-
too.
I feel like the V naught X really shouldn't be considered into play until you get to the top. of that.
Until it's a projectile. That's
Yeah.
exactly right. So I messed this all up.
Yeah.
The whole thing. I was going H at the, yeah, good. I'm glad you loved that because I was not happy with what I did. How many of you guys would think of that?
Oh, absolutely.
All right, okay. All right. All right, alert, alert, alert. We realized that we made a mistake here. So everything from here down, not that it's wrong, but we're going to do it. We're going to redo it on the next page. All right? So everything, if you look at this when it's bare, skip down here. Here. No. I'm going to put no, so if you just look at the notes, that you know not to look at that part, okay? See next. See next page.
There's another one.
All right. All right, so now let's think about this again. I knew that we hadn't incorporated 1.25, and Nick helped point it out to me. All right, so now what we need to do is get what we'll call V prime, okay? And we'll get V prime, and that will be our launch velocity, and that's the one that it's going to retain at the top, okay? So V prime cosine theta, so we don't get to do all that fancy trig stuff, even though it was kind of cool. I know, bummer, man. All right, so let's move along here. We got potential energy. I'm sorry, kinetic energy at the bottom. 1/2 mv squared, v naught squared, is equal to 1/2 m. We're going to call it v prime. This is the launch velocity. All right, we'll call it launch velocity. All right, launch velocity plus mg. This is why they did h1 plus h2, right? So what was that? That's h1, right?
Yes.
h1. Okay? So now v prime, which is what we're solving for. So 1/2 m, what's that v1? All right, 1/2 mv prime is equal to 1/2 mv naught squared, prime squared, sorry, minus mg h1, okay? Squared?
No, up.
The second one.
One half MV.
There we go.
Yeah, yes.
Thank you. All right, Culbertson's tanking it. All right, cancel the m's. All right, so now we get v prime is equal to the square root of, we'll figure this out in a second. We'll simplify it. 2 times 1/2 v naught squared plus g h1, right? And then we'll do that better. Square root of v naught squared plus 2gh, right? Mr. Culbertson's messing up bad today. Everybody use pencils. Minus gh.
One of these things on YouTube last night, my sister's like listening to, and I was like, Culbertson.
All right, so now v prime is equal to the square root of 49 meters squared per second squared minus 2 times 9.8 meters per second squared times h 1.25 meters. All right, calculator crew. What do we got?
Got something else in.
Thanks. 20, 25-ish.
4.5.
All right, square root of that, right? So 4.9. 4 point what? All right, 4.95 meters per second. All right, now this is our launch velocity. Okay, so now what we solve for will be the height above that 1.25. Got it? All right, so now for 15 minutes we've been working on this same problem. Now, it is a long problem. All right, any problems right now? No, I'm not trying to be silly. I just am. All right. All right, so now, new situation. So now we have, thing is leaving here with a velocity v prime, okay? It's got an x component, v prime cosine theta, and an x and a y component we don't care about. The only reason we care about that is because we still have that component up here as we've gone like this, right? And that's supposed to be at the top, so we'll fix that. All right, that's supposed to be at the top. And then we've got an additional height. This is like the water skier problem, right? Remember the water skier problem where we had V and then we had different and we solved for H? Okay, so we've got exactly the same thing going on here. So up here we have kinetic energy is equal to 1/2 m times v prime cosine theta squared, and potential energy is equal to mg. Now listen, we're taking this to be 0 now. Okay, we're taking this to be 0 just for this half of the problem, and so we'll call that h2. Okay? All right, so now at the bottom here we have all kinetic energy. 1/2 mv this squared, and at the top we have this up here. Not this, sorry, this. All right, so we got 1/2 mv squared kinetic energy, no potential energy. 1/2 mv prime squared is our energy budget. We're starting over. Is equal to 1/2 mv prime cosine theta squared plus mgh2. All right? So now we're trying to solve for h2. So we got mgh2. We can still get rid of all the m's, can't we? So let's do that. All right, so m and a m and a m. All right, so now we got, we want gh2 is equal to 1/2 v prime squared minus 1/2 v prime cosine theta squared, right? We are going to still be able to do the sine theta thing. Cosine theta. Awesome, I love doing trig. All right. We're doing all right there?
Yes.
All right. So h2 is equal to, let's see, v prime squared minus v prime squared cosine squared theta, right? I just squared everything in there, all over 2g. All right. So, continuing. Wow, this is a full feature film. All right. So now we got h2 is equal to, we'll pull out the v prime squared times 1 minus cosine squared theta over 2g. We get to do the sine thing again. All right, so we got h2 is equal to v prime squared times sine squared theta over 2g. You guys already using the calculators on this, right? h2 is equal to v prime, 7 meters per second, quantity squared. You're right. What was it? What? Should we go all the way back and plug in the expression for it? No! We really should, but we're not gonna. 4.95 meters per second, 50 times sine squared of 50 degrees all over 2 times 9.8 meters per second squared. Okay, meters squared per second squared. Good. Dimensionally, it's correct. What are we getting? H2 is equal to 0.73 meters. That means that our total, big H, is equal to 1.25 meters plus 0.73 meters. H is equal to 1.98 meters.
Whoa.
We did it, and it only took us 20 minutes and 24 seconds. Yay! Thank you, class.
New record.